When does a linear transformation preserve angles and length? So given any vector in the plane, we can multiply this vector by a matrix, a 2 by 2 matrix, and this will give us another vector. And this transforms two vectors into two vectors, and we call this kind of thing a linear transformation. And so what we're interested in this video is which matrices have the property that when I do this transformation, it preserves the angles and it preserves the lengths of the vectors. Okay, so let's take a slightly closer look at this question here. So when does a linear transformation preserve angles and lengths? What do we really mean by this? Well, I've got a little diagram here which will illustrate what we mean. So we have our two vectors x and y. These represent any two vectors, and they have a specific angle between them, alpha. And what we're interested in is when we multiply by this matrix M, we get two other vectors, mx and my, and they have an angle between them, beta. And what we're interested in is the condition when alpha equals beta, and when the magnitude of x equals the magnitude of mx, and the magnitude of y equals the magnitude of my. Great, so that's really the main thing we're looking into today. So the first thing that we're going to do is we're going to recall our best formula for the dot product, which is given here. In case you're interested where this formula comes from, you can see my video on the dot product, but we're just going to use it in a moment. So what we're going to do first is just investigate what is the dot product of mx with my. So using this formula, we have that this is the magnitude of mx times the magnitude of my times cos of the angle between them, and the angle between them is just beta. Great, so now I can use my assumptions. So if I assume that M is a matrix which preserves angles and lengths, in other words, it has that these two properties in yellow, three properties in yellow, then I can replace the magnitude of mx with just x, and the magnitude of y with just y. And the magnitude, well, not the magnitude, the cos of beta just becomes here cos of alpha. And guess what? This is just the dot product of x with y. And so here's the main point. We've just found that the transformations we're interested in have this interesting property that they preserve the dot product, which is a much more specific mathematical thing we can look at here. And in fact, this property that mx dot my equals x dot y, it implies these two properties here. It implies all of these properties here, here, and here. And you can try and figure that out yourself, or you can ask me and I'll answer it. But just to investigate this question a bit further, let's phrase it precisely. So given a matrix M, what we're interested in is when does it have the property that when I transform any two vectors x and y via the matrix, the dot product between these transformed vectors is equal to the dot product between the original vectors, which is just to say this condition up here holds. Okay, so we are going to answer this question. That's the main point of the video. But to answer this question, we're going to have to introduce a new concept, which is the concept of an orthogonal matrix. So an orthogonal matrix is said to be, well, a square matrix is said to be orthogonal if its transpose is equal to its inverse. So it has an inverse, and the transpose equals the inverse. So a rather peculiar kind of a property, but we have many examples. So first, most primitive example is the identity matrix, which is given here. So you can see the transpose equals itself, and then because the identity is its own inverse, this property here trivially holds. It's also quite easy to see that if you take two orthogonal matrices and you multiply them, you'll get another orthogonal matrix. So let's see how that works. If we assume that M and N are orthogonal, then we can consider the product of Mn and ask, is this an orthogonal matrix? Which is to say, is the transpose of this matrix its own inverse? And the way that we check if it's its inverse, we just multiply by this matrix, the same matrix that we're looking at, and we check, do we get the identity? Well, here we'll just get n transpose times m transpose times m times n. And this just gives us n transpose times n transpose. And why, sorry, not n transpose, just times n. And why is that? Well, just because this reduces to the identity here. And then similarly, this reduces to the identity. And so what we're left with is just that this is equal to the identity matrix. You can check this on the other side, but the point is that this product here is equal to the identity, and if I was considering mn times mn transpose, the same sort of argument will work. And that just shows us that the product of two orthogonal matrices is again an orthogonal matrix. Okay, so what is a concrete example of an orthogonal matrix? Well, in fact, any 2 by 2 rotation matrix is an orthogonal matrix. So let's see how that works. If I take r theta transpose times r theta, well, this is a certain product. It's the product of cos theta. Now, what does transpose do? It turns rows into columns. So the first row here is cos theta sine theta, so this becomes sine theta. And then the second row here is negative sine theta cos theta, so here we get negative sine theta, and here we get cos theta. Okay, so that's the transpose r theta transpose. And so let's multiply this by r theta, which is cos theta, sine theta, negative sine theta, cos theta, and let's see what we get here. So what is this equal to? Well, in the first entry here, I'm multiplying cos theta by cos theta. So what am I going to get? I'm going to get cos squared theta. And I'm going to add that to negative sine theta times negative sine theta. And so I get sine squared theta. Very nice. And then in the second component here, what will I get? Well, I'll get cos theta times sine theta plus negative sine theta times cos theta. And I'm sure you can see that that's equal to 0. And similarly here, what will I get in this component? Well, I get sine theta times cos theta plus cos theta times negative sine theta. And again, that's also equal to 0. And then lastly, in this component, I take sine theta times sine theta, so I get a sine squared theta. And I add that to cos theta times cos theta, and so I get cos squared theta here. Very nice. And this is just equal to 1, 0, 0, 1, which is the identity matrix. And so the reverse of this, so if I considered r theta times r theta transpose, this would also work, and that's all you need to know. So r theta, the rotation matrix, is an example of an orthogonal matrix here. Okay, now just before we give a nice description of orthogonal matrices, let's just take a look at matrix products. So here what are we doing? We are representing matrix products in terms of dot products by considering the rows and the columns here. So here we are going to think of this vector as this row vector here. The row vector of the first matrix, in the first row here is this x1. The second row is this vector here. And then the last vector in the nth component is this vector here. Then the y's here represent the columns of the second matrix. And why are we labeling these things? Because these are everything I've listed here is n-dimensional vectors. So we can consider the dot products between these vectors. And so let's take a look at what we get. If we multiply these two matrices, I take this I take this row and I multiply it with this column in that way. Well, then what will I get? Well, in the first component, I get exactly this dot product here. Now, I could have done that to the second column, and I would have gotten this dot product. And I could have done that also to the last column, and I would have gotten this dot product here. And so there's a pattern, and what this formula here represents is the full pattern. So given the rows of the first matrix and the columns of the second matrix as vectors, we can represent the product of the two matrices by this formula here involving dot products. Okay, good. So just keep that in the back of your mind, because now we move on to our main description of orthogonal matrices here, and that's what's given here. So given a matrix M, and we represent its columns as vectors here, C1 up to Cn. So C1 is the first column, C2 is the second column, and so on until we get to the last column, which is Cn. Then we have that this matrix is orthogonal if and only if these two conditions hold. So that is that the Ci's are orthogonal vectors. This condition here means that Ci, if I is not equal to j, is perpendicular or orthogonal to Cj. This means the same thing. Okay, now what is the second condition here? It means that the length of Ci is exactly equal to 1. So let's just read over this fact again. A matrix, if M is a matrix and C1 up to Cn are its column vectors, then this matrix is orthogonal, its inverse is equal to its transpose, if and only if the column vectors are mutually orthogonal and they all have length 1. And so what's the reasoning for this? Well, if we had to take the product of M with M transpose, which is given here, then the columns in M transpose, or the rows in M transpose are exactly the columns of M. So that using the formula that we looked at earlier, which I'll just quickly jump to again. So this formula given here, using this exact formula, where here we have M transpose and here we have M, then we can represent the product of M with M transpose in terms of the rows of M transpose, which are just the columns of M, and of course the columns of M. And so what is the result of doing that, applying that formula to the specific situation here? The result is that if these two conditions hold, in other words, Ci is mutually orthogonal with Cj, then the matrix product here, according to these two conditions, is just going to be the identity matrix. Why is that? Because if I take C1 dot C1, then this condition here tells me that this entry here must be exactly 1. But the same is true for C2 dot C2, because this entry here must be 1, according to this condition up here. And the same pattern holds if I go for all entries on the diagonal. I'll always get 1 because of this condition here. So where do the zeros come from? Well, they just come from this mutual orthogonality condition. If, for instance, I take the dot product here of C2 with C1, then according to this condition up here, we must get 0. And so that's what tells us that this entry here is 0. And all we need is that the indices are different, so that all these zeros appear for that reason. Okay, so if these two conditions up here hold, then M is going to be orthogonal. And it's very easy to see that if we had that M was orthogonal, we would also get that its column vectors are mutually orthogonal, just by the same argument, but in reverse. So this being 0 would force this dot product to be 0, and the entries on the main diagonal being 1 would force these dot products to be 1. And so that really explains this fact up here. Okay, so we have this interesting fact about orthogonal matrices, and they are given exactly by a matrix whose columns are form what's called an orthonormal set, which is to say they are mutually orthogonal, and they are unit vectors. Okay, good. Now, how does this answer the question which we had at the very, very beginning of the video? Well, let's take a look at that question. The thing that we're going to discover here is that if we have any matrix, then this matrix will be orthogonal if and only if it preserves the dot product. So just to go back to what we said earlier, the main question. The question that we began the video with was, given a matrix M, when is it true that this matrix, multiplication by this matrix, preserves the dot product, which is to say that this formula here on the screen holds. And so what we're going to see is that this is going to be exactly the orthogonal matrices. Okay, so let's take a look and see exactly how this works. So why is this true? So let's suppose suppose here that we are dealing with an orthogonal matrix, and let's try to show that this formula here will hold for any two vectors x, y. Well, it's quite straightforward. If I take m x and I dot that with m y, then by the way dot product works, we can represent dot product in terms of matrix multiplication, but it involves the transpose. So here we will take m x transpose, and then we'll just do ordinary matrix multiplication with my. Okay, good. Now we can use this formula for transposes, that this is going to be equal to this times m transpose times m times y. And here we can see what this is going to give us. The magic happens because m transpose is the inverse of m, so that this product here cancels to the identity. And what are we left with? We're left with x transpose times y. And the formula for dot product is that this is exactly equal to the dot product. This is exactly equal to x dot y. So in other words, every orthogonal matrix has the property that if I take the dot product of mx with my, that's the same thing as x dot y. Great, so that explains that orthogonal matrices preserve the dot product. Now let's begin with a matrix. Let's assume that we're going to suppose that M preserves dot product. Then let's try to see that M is going to be forced to be orthogonal, and let's see how that works exactly. All right, so we're just going to have to also look at a bit more theory here. So here's a small piece of theory. So what this is saying here is that in the vector space Rn, we have specific unit vectors. You don't need to worry too much about Rn and everything. The point is that we have these specific vectors, E1, E2, and En. Now these vectors are all mutually orthogonal. If I take Ei dot Ej, let's, for example, see what is E1 dot E2. It'll be very easy to see why this is happening. Well, I take 1 times 0, and I add that to 0 times 1, and then I add that to 0 times 0 plus 0 times 0, and so on. And the point is that we're just going to get 0. And we're going to get 0 as soon as I is not equal to j. Now, what if I took here, for example, Ei dot Ei? Well, also very clear what's going to happen. These are unit vectors. They have length 1. And so since this is the magnitude of these vectors, this is just equal to 1. Okay, good. So here's the main point. That's the first main point. Sorry, this is main point number 1. Now what is main point number 2? If I take any matrix X, let's say for instance the matrix given here. So the column vectors here are x1, x2, all the way up to xn. Then what are we getting? Well, we're getting that if I take x and I multiply it by ei, I'm getting the ith column of the matrix X. For example, let's take this matrix. Let's say we were dealing with a 2 by 2 matrix. So here we had x11, x12, x21, and here we had x22. And let's multiply by the unit vector, E1 and R2, and see what we get. Well, it's very simple to see what we're going to get. We're just going to get x11 plus 0 times x12, so we just leave x11 there. And then in the second component here, we have x21 times 1 plus x22 times 0. So we just get x21. And the point here is that this column is exactly this vector. And so the general statement is just what's given here. Okay, good. So multiplying a matrix by EI will give us the ith column. Okay, so let's go back to finish off the question we had earlier. So we are given, here's where we were. So we're given a matrix. We've just supposed at this point that M is a matrix which preserves the dot product. Now let's see that M would have to be orthogonal. And so what we're going to do is also assume that's for instance, the C, how should we say it, C1, C2, all the way up to Cn are its columns. Okay. So M preserves dot products, and these are its columns here. C1 is the first column, C2 is the second column, and Cn is the last column. Okay, now from this, what can we say? Well, if we take M, for example, if we take M EI and I dot that with M EI, I know that this should preserve the dot product. But this here is equal, so what does that mean, to preserve the dot product? It means just applying this exact formula up here. It would just mean that this is EI dot EI. And we already know what that is. We saw earlier that EI dot EI must be 1. But we also saw something else, which is that MEI is the ith column of M. And so we get that CI dot CI is equal to 1. So that's very good. We've already gotten the first condition here. Now for the same reason, let's take MEI dot MEJ. Well, preservation of dot product, again, just this formula here again, is EI dot EJ. And this is exactly equal to 0 if I is not equal to J. But again, by what we saw earlier, this MEI is the ith column, and MEJ is the jth column. So we have this. So what we've just discovered is that these two conditions are forced to be true as soon as we have a matrix which preserves the dot product, where the CI, C1, C2, Cn are all of its column vectors. Okay, great. So we've just answered the main question, but that just gives us a firmer understanding of what are the, well, exactly what is the answer to our question. That given a matrix M, when is it true that it preserves dot products, which is to say this formula is true? And our answer is exactly for the orthogonal matrices. All right. So thank you for watching, and I'll see you next time.